All right, good afternoon. Long weekend and Friday the 13th. Watch out for Freddy. All right, let's get started. Today we will begin chapter 4 and hopefully we'll end chapter 4. So we'll breeze through it. Let's bring up the notebook here. Transients. Okay. Transients are so called, or sorry, transient analysis is so called because we are analyzing the response of a system where the response is fleeting, it's momentary. Okay. Hence the name transients or transient analysis. After the transient response is finished or it's completed, all that's left behind is the steady state response. And this occurs only in inductors and capacitors. So we study three components in this class: resistors, inductors, and capacitors. All three are passive components. Resistors um, accept electrical energy, they oppose the flow of current, and they dissipate electrical energy in the form of heat. Capacitors and inductors will receive the energy, but unlike a resistor, they can store the energy. They store energy and they release it back into the circuit at a later point in time. So this energy transfer that occurs between these components, between the inductor and capacitor and the source or the circuit, that does not take place instantaneously. Energy transfer either in or out of these components takes a certain amount of time. And during this energy transfer portion, the voltage or current in the circuit is different at different points in time. Okay, so the response is transient, it's fleeting, it's momentary, hence the name transient response. Now, when you have one energy storage element in a circuit, we require a first order differential equation to solve it. Hence, it is also known as a first order circuit. If you have two energy storage elements, we need a second order differential equation, and that circuit is known as a second order circuit. Now, when we say it is a single inductor or single capacitor, we do not mean physically it's one single inductor or one single capacitor. It could be multiple capacitors, but we reduce all of them down to one single equivalent capacitance. So when we say one energy storage element, this one refers to the total equivalent capacitance or the total equivalent inductance. So we have one CEQ, one LEQ, first order circuit. If you have both in a circuit, CEQ and LEQ, or you cannot reduce it down for any reason whatsoever, then it's a higher order or second order circuit. Now, energy is being transferred back and forth from the inductor and capacitor. So when the energy flows into the components, we say that they are receiving charge. Charge is being built up. So we are saying this is the charging portion of the analysis, or the components are being charged up. When energy flows out of these components, then we say they are being discharged. So they're either charging or discharging. And the analysis during these charging and discharging phases is known as transient analysis. Transient response for a voltage and current, or charging voltage and current, is shown here. It always follows an exponential response. And we'll look at it again later on in the slide. But what we need to know for transient analysis is, where are we starting? Initial portion. And then where are we ending? The final portion. So I refers to initial, and F refers to final. Sometimes this is also referred to as zero. So II or I0 mean the same thing. The current at the initial point in time when we begin analysis, or current at time t equal to 0. Now, based on whether they are charging or discharging, we can classify these responses as two kinds, like natural and forced. And the word or the term force has a sinister connotation, but in this case, as applied to electric circuits, and there's nothing sinister. The forced response is simply the response of a system in when we apply an external source. So in that sense, everything that we have studied thus far, where we take a source, we connect it to a resistor, and then we obtain a resistor voltage or we obtain a resistor current, that was a forced response. External source present in a circuit, that is a forced response. When there is no source present in a circuit and all we have is stored energy, that energy is now, for that portion in time, is inherent in that component. It's not dependent on any other external source, and so energy is just being released, so that is known as the natural response. There's another term for the forced response or charging, which is step response. So we'll refer to step and natural. Simply put, if the source is connected, it's a step response. And if the source is disconnected, then it is a natural response. Okay. Anyone ever actually used a camera flash? Not the ones that are on our phones. The actual camera flash that's on top of like professional DSLRs. Yeah, I have. How many batteries did it take? Just two? Usually it's like 4 AA batteries or a special battery pack, like big capacity. But in those camera flash, you ever hear a whining sound or a whirring noise? What is happening is when you insert the batteries in, capacitor or the energy storage in that circuit is charging up. Once it charges up, it stores that energy. And when the shutter button is pressed, at the top of the camera in the mount, there are electrical connections. So when you mount the camera in there, underneath the flash, there are electrical connections that makes connection, well, electrical connection with the camera itself. You click the shutter button or you press that button, it obviously operates the shutter, but it also sends a signal to the flash, and all of that stored energy is released all at once to a light bulb, to a special light bulb, and there's a blinding flash of light, hence the name flash. So right there in that real life example, you have both step response and you have a natural response. As soon as the flash occurs, that flash starts charging up again, or that capacitor starts charging up again, and you hear that whining noise, and that's the charging portion. And when you click the shutter button, that's your natural response, releasing all at once. Okay, natural response circuits. You have one inductor, one capacitor connected to a resistor. Again, that single capacitor or single resistor is simply numerous inductors, numerous resistors give you a RL circuit, and numerous capacitors, numerous inductors together give you a RC circuit. If you have both, then you have a second order circuit, which is RLC. This is especially consequential or of importance because when you get to AC analysis, in AC analysis, the input voltage moves back and forth, meaning goes positive cycle, negative cycle, positive cycle, negative cycle. So when you have an inductor and a capacitor both in the same circuit, and you apply an AC source as input, what happens? In the positive half cycle, energy flows into the inductor. Negative half cycle, the energy flows out. But when the energy flows out of the inductor, it goes into the capacitor. In the positive cycle, energy flows out of the capacitor and into the inductor. So energy is now bouncing back and forth between the inductor and capacitor. Okay, and that's also labs 6, 7, and 8. Okay, 6, 7, and 8. There are some interesting applications when you have both R, L, and C in a circuit. Okay, forced response circuits, you simply have a source connected to the inductor and the capacitor. If we want to deal in terms of voltage, we'd have the Thevenin equivalent, meaning a source in series with a resistance. If we wish to deal with current, we'd use the Norton equivalent. Okay, so you have a current source in parallel with a resistor. All right, there are 4 circuits, and all 4 of them are very similar in terms of explanation and derivation. So we're going to look at the first one and then kind of like breeze through the next 3. Okay. All right. So here's the natural response. Now, in natural response circuits for a inductor and a capacitor, you will oftentimes see or come across the term a very long time. So a very long time simply indicates that the system is at steady state. So if you see or read the words for a long time or a very long time, it simply indicates steady state. Sufficient time has elapsed. That long time could be a few seconds, could be a few minutes, could be hours, could be days. We don't really know. We don't really care. All we need to understand that for a long time means there was sufficient time in the past that the system has reached full charge. It is now at a steady state. So in this case, the inductor was connected to the source IS because the switch was closed for a very long time. As the switch was closed for a very long time, that means that the system was at steady state. Inductor was behaving like a short circuit. All of the current was flowing through the inductor. Okay, inductor is fully charged, behaving like a short circuit. Now, at time t equal to 0, the switch is opened. When the switch is opened, circuit looks like this. Source is disconnected. Current is now discharging to that resistor R. And when it discharges to the resistor R, now we need to determine what the value of that current would be at any given point in time. So let's establish a few things first. Notations. Plus indicates immediately after. Immediately or right after. Minus indicates immediately or right before. Right after or right before. Time t equal to 0 simply means the time at which we begin analysis. We don't really care what it is. We are simply told at t equal to 0, switch closed or switch open, switch position, change positions, system changed in some manner, and that is the point where we are beginning our analysis. And when we begin analysis, we need to know what it is. So you can have t minus or t plus. It simply indicates the time right before or time right after. Initial conditions are established and noted by I or 0. So in this case, we can say II or I0. This is the initial current. And then IF is the final current. Okay, initial and final. All right. So how do we find that? Well, two things. Let's first talk about final. If it's a natural response and you're discharging, what is your best guess as to the final value of that system? 0. If you're discharging, the final value is always 0. It doesn't matter if that discharge gets interrupted halfway through. Okay, let's say capacitor is charged to 10 volts. It starts discharging from 10, 9, 8, 7, 6, 5, 4, and it's interrupted. It starts charging again. It doesn't matter. If you're writing the mathematical expression for that first portion of discharge, initial value is 10 volts, final value is 0. It may never reach the final value, but for the purposes of analysis, this final value is always taken as 0. Okay, so IF is always 0. In case of a capacitor, the voltage across a capacitor, VF, is always 0. Okay. So remember, what are we trying to do? We're trying to describe or derive an expression that would allow us to describe this curve right here. To describe this curve, we need to know the starting point, we need to know the end point, and we need to know the speed. We know it's always going to be exponential because the derivation's already done for us. So we need to understand how the system works. So if it's discharging, final value is always 0. The only thing that remains is the initial current or the initial value. For the initial current, here's the other fundamental thing. Current through an inductor cannot change instantaneously. Current through an inductor cannot change instantaneously, and voltage across a capacitor cannot change instantaneously. And so current at time t equal to 0 plus, meaning right after the switch is closed or right after the switch is opened, is equal to the current right before the switch was open. And right before the switch was open, it was behaving like a short circuit, which was IS, the total source current or the supply current IS. And so we can say a fully charged inductor, a fully charged capacitor would have that supply voltage or supply current, and that is the beginning point for our discharge. Make sense? All right, now in order to solve this, we apply KVL. From KVL, we know sum of all voltage should equal 0. So inductor voltage plus the inductor current, resistor voltage and the inductor voltage should sum up to 0. Inductor voltage VL is L di over dt. Resistor voltage is V equals IR. So we have a first order differential equation. Greater minds have come before us and have solved this. The solution has been known for many years, many decades. And the solution for this is I of t equals I0 times e raised to minus t over tau. That I0 could be II or noted as II in different books, but it simply stands for the initial value when we begin our analysis. And when we begin our analysis, that I0 was the fully charged value of that inductor current. So in here, we have 2 quantities to know: I0 and the time constant tau. The time constant tau for a RL circuit is always L over R. L over R. Unit for time constant is in seconds. So again, the speed of the energy transfer depends on the values of the inductor and the resistor. And that's it. That's the equation for discharge. Let's take a pause. Let me know if you have any questions. Okay, let's look at expressions for voltage. Voltage for the inductor and the resistor are the same because they're in parallel. V equals IR. Once you have the equation for I, plug it in, multiply it with R, and you obtain an expression for the voltage. Power is still the same, product of voltage and current. V square over R, or I square times R. Again, same standard expression. Total energy dissipated in the system is the total energy that was stored in the inductor. Remember from chapter 3, half Li square. Okay, half Li square. That was the initial current that was stored in the inductor. And that's where we begin. Okay. Let's look at the next three. Discharging RC circuit. At time t less than 0, switch was on the left, capacitor was charged, current flowed through the capacitor in this direction, and you had a fully charged capacitor. Because the capacitor had reached full charge, the voltage across it was VG. VG. Now, at time t equal to 0, switch flips from left to right. Source is disconnected. The only thing that is left in the circuit is the capacitor and the resistor on the far right. So you have a natural response circuit. Initial energy depends on the charge voltage. Voltage across a capacitor cannot change instantaneously. So voltage across the capacitor right after flipping the switch is the same as it was right before. Is the total generator voltage VG. That G does not mean anything, simply the supply voltage or the generator voltage or the input voltage or the source voltage. But exact same approach as the previous one. Apply KCL. Sum of all currents must equal 0. IC and IR sum up to 0. IC is given by C dV over dt, and IR is given from Ohm's law, V over R. And so we have a first order differential equation, again, the solution for which is already known. We obtain V of t is equal to V0 into e raised to minus t over tau. Exact same structure as the previous one. The tau is different. Tau is the product of R and C. If you've already done lab 5, pre-lab as well as the lab itself, you've already calculated tau. Tau is R times C. Okay, R times C. Equations for current, power, and energy. Current can be found from Ohm's law because it's a series circuit. Same current goes through both. Power is again product of voltage and current. P equals VI, V square over R. And total energy stored in the circuit, half CV square. Half CV square. The next page is a summary of the approach, but I'm going to skip over that because there is another summary page later on that describes all four circuits. Okay, so we have two more circuits. Again, very similar. This time we have an inductor. We are charging it from a source. Source is Vs, the resistor R. Initial energy, again, we don't know what the initial energy is. The inductor could be charged, it could be discharged, we have no idea. It may be provided in the circuit. If it's not, you simply assume it to be zero. If nothing is stated about the initial conditions, then you assume it to be zero. So this time you have a source. So when you apply KVL, VR plus VL is not equal to zero, it's equal to Vs. VR Ohm's law, VL L di over dt, solve the equation, solve the differential equation, and you obtain an expression. And this time, you have a third expression, IF. IF. I0 is the starting point, IF is the end point, and tau is the speed of the transfer. Tau is still the same for an RL circuit, it's L over R. That does not change. If we are working with a Thevenin equivalent, we can use the voltage. If you wish to find the current, simply apply Ohm's law. And then same thing for the capacitor circuit. You have a capacitor, start charging, initial voltage depends on the initial stored energy. If it's not stated in the problem, it's not provided, assume it to be zero. Final value, of course, would be equal to the voltage or the current that's being supplied. When you apply KCL, this time IR plus IC equals IS, not equals zero. Solve the differential equation. And again, you have three terms in there: starting point, end point, and the speed of energy transfer. Final value of the voltage, and we obtain from Ohm's law. And time constant remains the same. For an RC circuit, it is the product of R and C. All right, so why did we breeze through all four circuits? Well, because of this. This is the one equation to rule them all. We have XF, we have X0, and we have tau. Okay, this is, as I said, this one equation describes all four circuits. XF is simply the final value. Xi or X0 is the initial value. And of course, we have tau is the time constant. These are the only three quantities we need. Okay. X stands for voltage and current. If you're analyzing for an inductor, we like to think in terms of current. So X would be current, I. So it would be II and IF. If you're analyzing for capacitor, it would be voltage, it will be VF or VI. Okay. So let's see how this would fit for a natural response or a discharging response. For a discharging circuit, what did we say? Final value for a discharging response is 0. So XF would be 0 for discharging circuit. So the equation would reduce to X of t is x0 into e raised to minus t over tau. Compare it to the first two expressions we found. It's exactly the same. You have a stored energy in a component, and it's slowly being discharged. So if x0 was 10 volts, and your time constant is 10 seconds, well, after the first, no, sorry, not 10 seconds, 5 seconds, let's say. So after the first second has elapsed, it would have lost 63% of its charge, only be left with 36%. So from 10 volts, it would drop down to 3.6 volts right after 1 second. E raised to minus 1. Okay, e raised to minus 1, which would be one time constant. And of course, if you're charging up, then you need both initial as well as final. Now, when you're charging and the initial value is not provided, or if it's provided and says there's no stored charge, then x0 is 0. Then your equation reduces to xf minus xf into e raised to minus t over tau, meaning 1 minus e raised to minus 1, 2, 3, 4. So now you have a rising exponential curve. That makes sense? So now let's take a pause. You think over this and you let me know if you have any questions. Any questions at all? I'm sure there are lots of questions. Again, transient response, meaning the energy transfer phase in a circuit, whether the energy is flowing into the components or out of the components, it always has an exponential form. If it's flowing into the components, we say it's charging. If it's flowing out of the components, we say it's discharging. If you wish to write an expression or equation for this portion of the analysis, we need a starting point, we need an end point, and we need the speed of this transfer. So starting point x0, end point xf, and the speed, which is tau. That's it. If you figure these three out, then you can apply, for most circuits, you can apply this generic solution. One equation to rule them all. Tau doesn't change. For a RL circuit, tau is always L over R. For a RC circuit, it's always R times C. Okay, R times C. No questions, okay. All right, so when we plot this and we saw these waveform, it should look like a blank page. There you go. When it's charging, it's a rising exponential waveform or a curve, and when it's discharging, it's a falling exponential curve. Okay, and when we tabulate and plug in the value for t as equal to 1 tau, 2 tau, 3 tau, we obtain this table. More than 50% of the energy is either lost or acquired within the first time constant. More than 60% actually, as you can see here, 63.212. Okay, so after the first time constant, either acquires or loses more than 60% of the energy. Now, mathematically, of course, if we plug in any value of tau in, any value of time in there, we would never approach zero. We would never, mathematically, we would never approach full discharge or full charge. But by standard accepted convention, we put a stop to it after 5 time constants. This is 99.3. Okay. So the homework for this chapter is homework 14. It was due on Sunday. Because Monday is a holiday, I've pushed it back and I've made it due on Monday instead of Sunday. At the end, there are 3 slides with 3 examples. And all of these examples were, they are solved in detail. You can take a look at these. These are actually from our EE major class. This is not something that you would see in 201. This is from 211, which is for our EE students. But nevertheless, these are really good examples. This one specifically is not. This could apply equally to both EE and non-EE students. Okay. Talking more about this one, where you need to find I0, which splits between 2 resistors. Other than that, it is still a first order circuit, only one component, and the same thing here. Still a same first order circuit. There's no difference. But definitely go through these examples. Reach out to me if you have any questions. I will be available over the weekend via email and via Zoom if you need. And then quiz on Wednesday. Again, quiz schedule has been online since the beginning of the quarter. At this point, I'm assuming everybody has taken a look at it. So quiz on Wednesday based on chapter 3, not on chapter 4. Okay, on chapter 3, which is fundamentals of capacitors and inductors. That is homework 13, not homework 14. I'll leave you with this real life example. In every rectifier circuit, we use a filtering capacitor. Okay, meaning every electronic device that you see, every laptop adapter, mobile phone charger, tablet charger, computer, monitor, projector, power supply, televisions, there's a power supply, and in that power supply, there is a filtering capacitor. That filtering capacitor is used so that it smooths out the AC, like AC waveforms, right? A diode first rectifies it from positive negative to positive only, and then it passes through a capacitor, which flattens out the response. The way it works is when a positive cycle arrives, the capacitor charges. That charging is very quick, and then it starts to discharge. And the discharge is very, very slow. So it charges up, maximum charge, and it starts discharging very, very slowly. Remember what I said, if it reaches, let's say 10 volts, eventually, if you just leave it to discharge, it will eventually discharge all the way to 0. But with the way these circuits are designed, that discharge is interrupted. It would barely lose 0.1 volt. So it's fully charged to 10. It might drop to like 9.9. And the next positive cycle arrives and it starts charging again. So it's a continuous cycle of charge, discharge, charge, discharge, charge, discharge, and it only falls less than 100 millivolts, 0.1 volt, or even smaller than that if you want a full flat DC line. So if you were to analyze just that portion, you would say, okay, it's charging, right? That's the step response. Then it begins its discharge. And to analyze the capacitor performance right in there in that small window, we would still take the final value as 0. The final value never arrives, of course. It will stop at 9.9 and begin charging again. And that's inside every device that we use. Okay. All right. So we'll end class here today. We breezed through it. We still have 8 minutes left. I'm happy to stay around and answer any questions you may have. Otherwise, you're free to leave. I will see you all on Wednesday.